Okay, so this video is about basically critical path analysis. So we're going to be creating networks from activity tables and then looking at the critical path. Basically what that means is we're looking at minimal time in which a project can be completed. We can use networks to model this. So basically we can use this type of network for any multi-stage complex process like a lot of business projects, to ensure completion in minimal time. That's what we're after. Having it done quickly, having it done efficiently, and having it done with the least amount of cost is what any kind of business is after. What it basically takes a form of a flow chart, so it becomes quite linear with some bits around, as we'll see shortly. So the arcs of these sorts of networks represent activities and the time that it takes for those activities to be completed. The nodes indicate the start and finish of an activity, so the end of a particular activity and the start of the subsequent activity. Immediate predecessors, so this is basically the tasks or activities that must be completed before the next one can start. So a good example of that is the activity chart that we have here. We have just a nice simple one that I'm going to go through and do an example with you for. So activity A has no immediate predecessor. There is no task that must be done before A. Task B, though, cannot be completed until A has been completed. Then we have task C, which cannot be completed until also A has been completed. Activity D also must only start once B and C have been completed. And because they can't start until A has been done, we won't be able to start D until A, B and C have been done. So what we'll do is we'll start with A. So because it has no immediate predecessor, this is the start of A. It's directional, so we can give A a little node. That's the beginning. Then task A has been completed. This is now the end of task A before B and C can actually begin. But now B and C, now that A is done, B and C can both start. That means we can actually do it this way. And our finish point. So B and C. Which way doesn't really matter, it just sits that way. Now that B and C have been completed, they're our immediate predecessors for D, we can now do task D. So you can see here, task D. So we have our beginning through to our ends so far. Now we have our nodes representing each of our start and finish points. These arcs with direction showing us the way that they are heading. So this is beginning and end, beginning and end, beginning and end, beginning and end for each of those tasks. So B and C don't actually depend on each other, so they can be worked on simultaneously. So it's multitasking. So because they don't depend on each other, they can work at the same time. But task C is actually shorter than B by 2 minutes. How do we know that? What we're going to do is we're going to add some time into this one. So on the end here, just going to add in some time and show you that. So in our time, we'll make A 5 minutes, B 4 minutes, 2 and 3 minutes for the last two. So these two simultaneously, not a problem, but C, shorter. Okay, so by 2 minutes, so it can actually, C can actually be started 2 minutes later than task B and still finish at the same time as the other. Okay, so let's give this one a bell. Feel free to pause the video first and then you can have a go at this first and then come back and have a look at this, but I'll go through and answer now. Right, so let's start with A. So we'll put A over here. A, which is 5 minutes. Yep. Okay. Now, A must be completed for B and for D to start. And then we can, okay, so B can start. Let's do B, which is 4 minutes. Now that B is done, D can also be done. Actually, yes, it can. D can also be done. So what we might do is we might do those simultaneously. So it looks like B and D just have to have A done, so we can do these simultaneously. So B at 4 minutes, D at 3 minutes. So D could actually start a little later. Okay, so now we've done A, we've done B, we've done D. So that means these two, E and G, can happen. We haven't done C yet because it still needs to have E and G to happen. Okay, so now that D, we can do E and G. Now again, they could be simultaneous. They can happen at the same time. So E, which is 2 minutes, and G, which is 2 minutes. E and G done with our D's. Okay, so A's been done, B's been done, D has been done, E and G. Okay, so that means we can now do C, F and I, and they can technically all be done at the same time. So C, F and I. C, all of them going this way. So C, which is 6 and 4. So actually I might make this one, it already looks a little longer. We might make this one C because it's only 2. F is 6 and I is 4. Okay, so now C, F and I are done, and that's I done and C. Now you can see that H has to be done last because it needs to have J done, and J can only now be completed because C is done. So now we can go J, 1 minute, with our arrow, and H, 1 minute. Okay, and that is our pathway for this network. So A all the way through to J, but actually ending at H because of the way that the task needed to be completed. You can see that we've got multitasking happening at a couple of times here with these 3 being done at the same time, but because they're different times, they could actually start and finish at different times. And that is an excellent place to stop because that is what we're going to lead into our next video, where we look at forward and backward scanning and actually planning out the time it will take for such a project to be completed, the minimum amount of time when things can start and finish.